All right. Hello, everyone. This is going to be a presentation about IoT hacking, presented by me and Draden. Let's get just a short introduction about ourselves. Hello, my name is Tenchi. I'm from Las Vegas. BS CSEC, minor in math, third year, the captain. Windows is lovely. I'm retired, and I'm an incoming red team intern at SRA. So, let's go. All right, let's get this Draden guy up here.
Hello, I'm a CSEC freshman. I'm an avid CTF enjoyer, like some certain black teamers. I'm in Contagion red team and ISTS black team. So we're going to get started by talking about what is IoT. Tenchi's going to clip this on for me. IoT stands for Internet of Things. You may have heard about this before. It's a big and growing industry. We're going to go over some terms here and some of our favorite acronyms. ICS stands for Industrial Control Systems. OT stands for Operational Technology. ICS is a subset of OT, which is part of IIoT, which is Industrial Internet of Things. SCADA stands for Supervisory Control and Data Acquisition. HMI stands for Human Machine Interface. Nodes are sensors or control systems that we use in IoT, and PLCs are programmable logic controllers. We'll get into some of the protocols that use these in a moment. So why is IoT important? The tens of billions of new IoT devices will exist by 2025, which is expected to increase the global GDP by tens of trillions of dollars. And IoT impacts safety. IoT is part of autonomous vehicles, so self-driving cars, locks that people are putting on their houses, cameras, healthcare devices like insulin pumps and drug infusion pumps. So the safety of these is critical if it's going to improve the economy or be useful at all. So we're going to talk about the protocols now. It's just an overview.
Yep, so this should be a short overview, but the first protocol we're going to cover is SPI. So SPI stands for Service Peripheral Interface. This is mostly used in embedded systems for short distance communication. So it's a duplex, so it gets, you can send both data from both ways. It was designed in 1979 by Motorola. So if we take a look at this diagram right here, so the 4 wires, but this is the SPI controller for this one is setting to 2 separate peripheral devices. So it has a clock, an output and input, and the chip enable set, which is also sending data to the peripheral devices. So very simple, straightforward. You got input output from the controller to the peripheral, and the clock is used for reading the data and timing the data correctly. Okay.
Next is integrated circuit, also called I2C. This is a serial communication protocol for low-speed devices, and was developed for communication between devices on the same board, but it can also be used with components connected via cable. It's used by sensors in a lot of ICS devices, and it's a more simple protocol than SPI, which we just talked about, because it uses 2 wires and was developed in 1982. Here's an example diagram of that. Modbus was developed for use with PLCs. It is openly published and royalty-free. Protocol offers no security against unauthorized commands and data interception, and the transmissions are contiguous, which means that any master server station needs to be able to handle buffered input. This was developed in 1979 by Modicon. PLCs use something called ladder logic, which has become a programming language for PLCs, which are based on a diagram of physical components, and they get complex very quickly. If you'd like to know more about the damage that this complex stuff can cause, ask Fred about what happens if you change an R to an S. The answer is millions of dollars in damage.
All right, next up we got Bacnet. So Bacnet stands for Building Automation and Control Networks. This was developed in 1987 by the American Society of Heating and Refrigeration and Air Conditioning Engineers, which is located in Tennessee. Now their headquarters is in Atlanta, Georgia. Designed to allow communications of control systems such as HVAC, as the acronym of the people who developed it, HVAC, lighting, security equipment, and fire detection systems. And funny enough, that this whole building is also powered by Bacnet, so very cool stuff that can be done with this building as well. Okay, so this is just an example You're going to see a lot of proprietary or open source alternatives to a lot of these IoT protocols, but in this case, we have a Bacnet over IP, which is kind of the control system. So we got a little server/client, and also a Bacnet router in between that is controlling our nodes. So that's going to be two, what looks like two temperature sensors. So this is an example diagram of how Bacnet is being used. Just a quick note, probably should include this in later slides, but Bacnet, so there was a really interesting news article that I read where a building automation engineering firm was hit with a cyber attack, and they lost contact with hundreds of sensors in their building automation systems, which is also synonymous for Bacnet. They were also using their proprietary protocol called KNX, which is a European company that develops their own Bacnet nodes, and they were able to do this through leaking the bus coupling unit, which controls the Bacnet security, and they bricked all the nodes within the VAS. So there's some very cool stuff with IoT security, and we're going to talk more about that in the later slides.
It's the wrong way. The wrong way.
Wait, what was it going that way?
You were pressing the left one. So DNP3 stands for Distributed Network Protocol 3. It is a set of communications protocol, and it's used between components in process automation systems. It was designed for use in the electric utility industry, and it has been adopted by water utility companies as well. This is crucial in SCADA systems, and this, like Modbus, is open and public. And here is an example diagram of using SCADA and DNP3. Next, we're going to talk about how to attack Internet of Things devices and some different general types and forms that you'll see.
Okay, so first up, we're going to talk about some signal jamming attacks. So this is when you're interfering with communications between two systems. This can be leveraged to do denial of service attacks with signal jamming. You can isolate control servers and clients and affect multiple different nodes. So in this example, this is with kind of the autonomous cars example, where the car is traveling down the road and it's receiving the signal, but then a malicious signal is sent to deter the car elsewhere. I think you've seen multiple examples of these as well. Another example is during the CPTC 2020, where they sent a ping flood to a Modbus controller that was simulating a dam, and that caused the entire dam to overflow and cause millions of damages. So it is very real and very disruptive. Replay attacks?
Yeah. So replay attacks repeat an operation or resend a transmit signal or packet. So the idea is an attacker will capture a user's legitimate use of some sort of IoT device, and this can bypass authentication if it is bad or non-existent. It's typically severe whether or not it affects IoT. So you also see this in other kinds of wireless attacks for Wi-Fi. In the past, there's a project that some RIT students did about a year or two ago where they actually captured a signal for a Bluetooth lock and were able to just unlock it whenever they wanted. And they also did the same thing for controlling a Bluetooth lamp. So they could just turn on a rave whenever they wanted, which was very interesting. Next slide. In the news, we have seen the Medtronic MiniMed 5-way insulin pumps recalled in 2019 under ICS Medical Advisory. This had an associated CV with it, with a base score of 8.8. This used a replay attack. You can see all of the different pumps that were recalled from that. You could change the settings to choose hypoglycemia or hyperglycemia, and it was fairly simple. There were about 4,000 people at the time that used the pumps, though it is not known that any of them were harmed because of this vulnerability.
So next up, we have settings tampering attacks. So this is very similar to replay attacks, kind of what Draden was talking about previously with the insulin pumps. Exploiting a component's lack of integrity, changing the settings to produce an unexpected or malicious behavior. And so the extending the control server with change the drug used in a fusion pump, or in Draden's example, with the insulin pump introducing hyperglycemia or hypoglycemia. So a little mitigation and a little nice diagram that I found was this ARM IoT device and enabling this ARM trust zone, which kind of has this whitelist functionality to that is mapped to these certain addresses for function A, B, and C. And a nice presentation was done by the ARM trust zone by a previous RITSec member. I'll also be linking that in the RITSec research channel. So very, very cool stuff. A lot of alumni did amazing research before. And we're going to talk about our next attack.
So node cloning creates fake nodes in a network to compromise the reliability. It subverts poor reputation systems, and it can lead to a denial of service attack. It can also propagate false information to other nodes on the network, and if you're able to create a node that acted as a master server, then you could gain control over the legitimate nodes. This is typically called a Sybil attack, and it's also sometimes called a 51% attack, where if you gain a slight majority control, 51%, you can take over the network. You can mitigate this by increasing the cost of generating identities and require a chain of trust linking nodes to a trusted entity. Here's an example diagram where you can see there's like an honest node surrounded by bad guy nodes, but there's only like one link to legitimate nodes. Are there any questions? Yes, Kenny. Drones are also cool.
Drones are cool. Any questions? All right.
All right, we'll wrap it up. We've got some resources if you want to learn practical IoT hacking. Great book. Thank you.
Thank you, O'Reilly.
Yes. Oh, yeah, just to mention, O'Reilly has a lot of free books with the RIT email. Very helpful. All right. Thank you.
Thank you.